comes to us from Chapel Hill. Prior to that, she was at the University of Maryland, overlapped a little bit with our own Dr. Catherine Birmingham, who had started as a postdoc as Xiao-Ming was finishing up her PhD. Xiao-Ming's major advisor or primary advisor was Dr. Roberta Rudnick at Maryland. She also worked with Bill McDonough. Knows James Farquhar and was one of many who wanted to work with Rich Walker and probably worked with Jay Kaufman. And you don't know this, but we went to high school together.
Oh!
So small world. Throughout her career, well, prior to Maryland, she was at the University of Waterloo where she got a BS, and then also it was paired with a dual program, so she has 2 bachelor's degrees from the University of Geosciences, which was in Beijing, but now is in Wuhan. She has published with many people that we know, and they include Bob Hazen, where she did her postdoc at Carnegie before going to UNC Chapel Hill. She's published with Jay Kaufman, Anat Shahar, who's at Carnegie, Tim Lyons at Riverside, Andy Knoll at Harvard, just a whole list of people, including Peter Schwartz, who I've sailed with twice on the ocean drilling program expeditions. And without going any further and taking any more of her valuable time, I hand it off Xiao-Ming Liu.
Well, thank you. Thank you, Jim, for your very nice introduction, and thank you all for coming to take this geochemical adventure with me. So, yeah, let's start. Actually, I'm not going to talk about any papers that Jim just talked about. So I'm going to show you what our group have been doing in the past couple of years, pioneered by my first few students and postdoc. So first thing first, I know some of you are not geochemists. I'm a geochemist by training. So just give you a little bit of introduction what geochemist does every day. We're not the lab rat doing the pipetting every day in the lab. To some degree it's true, but we actually study decomposition processes, cycling, evolution of the Earth and other planets as well, right? So we have subject of cosmochemistry, for example. For those of you who are, I know you are an undergrad, yeah? So I think my take-home message is hopefully to you is geochemistry is cool. So if you don't remember anything, please remember these 3 words. Okay, so why do we care, right? So we're coming from a habitability perspective is everyone we're meeting here is really lucky. Why we are so lucky to have this blue marble? This was taken a couple years ago by NASA, remote sensing satellites. It used to be the Apollo 17. They did it in 1972, right? The first blue marble sort of thing, right? So that's our Earth, right? We have a life, we have a good water cycle, right? That's good that we are happy here. It wasn't like this, right? Just 4-point-something million years ago, right? So this time period in Earth's history, we call them Hadean, right? That's hill-like environment where their Earth's surface was still forming. We have continental crust is still cracked, was bombarded by meteorites and asteroid, and those volcanoes have a lot of toxic gas released into the atmosphere. It was hot and kind of thick gas, right? At least it's not suitable for life as we know it, right? So that was the early Earth. So habitability in Earth's history, it's like this, right? It wasn't really easy to get it here, right? And also, if we look at the space, right? Earth is in this perfect Goldilocks principle, right? It's not too close to the sun, too hot like Venus, or too far away like Mars. So we are in this best habitable zone, at least for the life like us. The other advantage is if you look at this plot of Earth's surface temperature through the past 500 million years versus the average surface temperature, you will see our Earth's surface temperature is relatively stable, right? Not moving too much, below, sort of above freezing for sure. So we have liquid water. And also the fluctuation is not that much, 30 degrees is not too bad for a planet for 500 million years, right? So we are lucky in terms of having this perfect temperature for habitability. That goes back to, the habitability is actually on the geological timescale is maintained by the long-term carbon cycle, right? So we have this carbon cycle, for example, two important components is, the carbon dioxide released by volcanoes, and they get into the atmosphere. Some of them actually, dissolve with water, forming carbonic acid, right? This is kind of too weak for us to use in the lab. Geochemist doesn't use this, but the Earth has a lot of time, so we can actually use carbonic acid to react with silicate minerals. So silicate mineral weathering is actually the net output for the CO2 from the atmosphere, at least in the long-term timescale. So basically, chemical weathering, now we're talking to the topic, what I'm gonna focusing on today is chemical weathering. So chemical weathering actually is the connection between the Earth's interior process, the volcanism, the tectonic uplift, with the surfacial climate conditions and the long-term carbon cycle, right? So chemical weathering, especially silicate rocks, is important in connecting the interior Earth and the surface Earth. So that's why we care. How many of you are graduate students? Okay, maybe some of you are still looking for your dissertation topics, or you already know what to do. You probably, looks like you already know what to do. But good, good for you. I wasn't sure. So when I started, I was a master's student at the University of Maryland. I was trying to be ambitious. I want to use math to solve earth science problem. So I started my master doing fluid rock interactions, in the pegmatite into the country rock. Then I realized my modeling skills wasn't so great, and I can tweak the model to have various results. I thought, I have some doubts. But then I took a class with, at that time, my PhD advisor, Roberta Ranick, on origin and evolution of continental crust. And then there was a paper on how chemical weathering and associated erosion can changing the crustal composition. Because there is for those of you who are not petrologists, there is a long time paradox in petrology is the continental crust, on average, the crustal composition is more like andesitic to felsic, right? It's like your granite rock, a little bit lighter, right? But the building block, at least the current day arc settings, like those are not drawn by my son, it's me, 12 years ago, something like that. But anyway, was basalt, right? So the crustal composition paradox, people usually explain it as a recycled crust differentiation and recycle from the bottom, right? So that's the thing. But then one paper actually published in 2008 that's saying maybe continental weathering and and associated erosion is important. But how important is important, right? We need a way to quantify. So at that time, I was doing lithium isotope study, and then I used lithium isotope as a proxy of weathering and associated erosion. So we quantify that at least 15% of the original so-called the juvenile crust, the original crust, is lost due to chemical weathering and erosion over the whole Earth's history, whenever you believe that plate tectonics started or the continental crust formed, but at least like 3 billion years over this time, right? You think it's important, right? 15%, but it's actually controversial, and this actually idea kind of go against with my own advisor's previous paper, but she didn't find any problem with the math, so she said, okay, we can publish it. So that's why you have this cartoon. So as always, you keep open-minded, right, with what you want to do. So I went to Maryland. I want to do really hard rock and maybe mantle crust, cycling. End up to be interested in superficial processes because chemical weathering preferentially remove soluble elements like lithium, potassium, magnesium that could be, getting the dissolved elements into the ocean, right, and leaving the crust to be more silicate rich. So that could be one thing. So that's why that changed my whole career trajectory, that I want to study weathering, one of the aspects at least. Then I'm into a field. How many of you, are you here, everyone here probably heard of lithium isotope, right? Because of Linda, right? Right. So at that time, like a couple years ago, even at that time, I didn't hear of lithium isotope as an undergrad, because usually you have isotope system like carbon, oxygen, right? That's a so-called the traditional stable isotopes. And then there is a new field. Just when I'm getting into graduate school, okay, still works. There is a group of element pioneered by the starting of mass spectrometry, ICP-MS, right? Inductively coupled mass spectrometer. It's a mouthful thing to say, but you have those, multiple of them in this department, right? So they actually specialized in analyzing so-called this non-traditional stable isotope system. Many of them are actually metal, right? So at the start, about 20-something years ago, people don't know what to call them. They call them non-traditional stable isotope. Probably not so good, right? At some point, it's becoming traditional. but anyway, so we're struggling with the name, but still, some people like to call them metal stable isotopes, although some of them are not metal, but anyway, most of them are metal, I guess. So it's hard to name those group of elements. So they're actually very useful, even for environmental geochemistry application. For example, the chromium isotope have been used to trace groundwater contamination, and then mercury isotope is bioaccumulation, right? The fish can eat the plants that contaminated by mercury, so you can use mercury isotope to trace contamination. So I want to mention only. I don't want to give you a list. That will take 5 hours or more. So I want to focus on the two that I'm more familiar with. Lithium isotope I have been working with since graduate school, and then potassium isotope is the newer-ish, the more non-traditional stable isotope when I started at UNC. So what is isotope? Still remember, right? An element with the same number of yes, you're brave. Good. Yes, so that's good. Yeah. So I was just quizzing. Make sure you don't fall asleep. Good. I know it's hard. It's under pressure. You did well. Okay. So for lithium isotope, right, the same number of protons and 3, but different number of neutrons is lithium 6. Right, has 3 neutrons, and lithium 7 have 4 neutrons, right? So they have different mass number, right? So 6 and 7. The reason we like those light stable isotope is the relative mass difference is significant, right? Assuming if you have no idea, 6 versus 7, thinking about you are lifting, if you have a wrestling competition between 120 kilo person, oh no, too much. 120 pounds person versus 130 pounds, right? So they are not in the same match, right? So they have like about 17% mass difference, right? So big. And potassium isotope also have 2 stable isotope. One is 39, one is 41. So they actually have a little bit higher difference because they have 2 mass unit difference, right? So 41 minus 39, and then divided by around 40. So you still get 5%. Roughly mass difference. This kind of thing are good for isotope fractionation, right? How many of you haven't heard of term isotope fractionation? Everyone heard of? Good. That's good. So for lithium potassium isotope, they are especially useful for chemical weathering study because both of them are soluble elements, so they can be removed by water, right? But then some of them actually made it into clay, so they actually stick into the solid phase. In the meantime, we have this isotope fractionation because clay mineral has a tendency of taking the lighter isotope, and the water is usually heavy. But we'll talk about mechanism later because we have different explanations for different things. But in general, just give you a little bit idea. And also why lithium and potassium are great is, we're going to use this for one application I'll tell you later, is they are both enriched in silicate rocks. So they are great for tracing silicate weathering, right? So things like strontium isotope, sometimes they publish a record or Earth's history, then they say, oh, how about carbonate weathering, right? So that influences carbonate weathering a lot. So both of them are actually extremely enriched, about 2 order of magnitude higher in concentration in silicates versus in carbonate. So they are great tracers for silicate weathering. But there's another enemy later because they are so low in carbonate that we want to use marine carbonate, and then it's harder to deal with. But that's a later problem. And potassium is a nutrient, lithium is not a nutrient, just something for fun that influenced the biogeochemical cycle a little bit. That I won't be talking too much, but we'll do it. So hopefully by this point you are eager to know how we do it, right? For those students, all right? So you want to measure lithium and potassium isotope. For those of you who are a little older, that's Breaking Bad. Remember those? They are trying to destroy the bodies using HF, right? Not a good idea. I would just use nitric, right? You don't need HF. It's overkill. You don't really need dissolved rocks, right? We are not made of silicas. But I'm just trying to say this is not a straightforward mechanism, especially when we actually trying to dissolve carbonate rocks. We can't use HF because then we get all the dirts. Forgive me saying that. All the silicas contamination like into the carbonate, right? So we need a good protocol to actually extract, hopefully, only the orthogenic carbonate from the rocks. So we can't be like those bad guys. So we need to develop a good leaching protocol to actually get the component we want, right? So actually, there's a backstory. My students, actually, first student, she spent many years in the lab trying to do this. I thought, oh, this is an easy project. You just do it, and then you have a project complete. I have a paper. Then actually, it takes 4 years to actually get this paper. So I'll tell you what's the problem there. It's difficult. The other one is many of you have experience with column chemistry. Oh yeah, I call it character building processes, right? You are nodding, because we need to separate the elemental interest. For example, here lithium from the rest of the rock, right? The rest of the rock are made of, aluminum, iron, manganese, magnesium, calcium, all that, right? Only concentrate a little bit lithium, right? And this is a tedious process. And the column itself, if I'm not careful enough, I produced like hundreds of isotope fractionation when I was first doing this. And I was excited. I thought, oh, I found some unnatural fractionation. I show it to my advisor. She said, do it again. Doesn't look like it's natural. But anyway, sounds like contamination. Yes, I couldn't reproduce that 300 value for lithium isotope because maybe I was one step late collecting the acid, because you need you could have fractionation on the column. So you really need to get 100% almost, or 99.9 of lithium out of your column, or potassium, or any of those isotopic system. So here we actually work with Rutgers many years ago. Linda was on our paper when we tried to set up our column chemistry. We work with Linda on this multi-collector ICP-MS. Then, actually, I don't own a multi-collector ICP-MS. It's super expensive, and I need expertise to run it. So we were able to do this. I call it poor women's geochemistry. You had a question? No? Okay, just read. Okay. Yeah, so because we can use a quadruple ICP-MS. The ones you also have is called ICAP. It's kind of cute, ICAP cute. So it's it's a smaller one. The difference between the multi-collector is you have multiple Faraday caps collecting isotopes at the same time, right? You can do lithium 6, 7, or if there's lithium 8, 9, 10, you can collect them at the same time. So you can minimize the ratios, the noise, the fractionation in the instrument. With quadruple, you had to jump mass really fast. So you can only measure one isotope at one time, but you can jump, 0.seconds, right? So lithium 6, lithium 7, lithium 6, lithium 7. You just have to jump really fast. You can still do it, although the accuracy, I would say, is not as good. So it's about 1.1 for our lab in longer term. But it's not too bad. Consider this machine is very easy to run. Even undergraduate student has used my machine to do elemental concentrations, right? So it's not that crazy. So it's only 20% of the cost of multi-collector. So, and you get twice worse precision. So I guess it's an okay deal. And also for the question we analyzed in the ancient history, actually the fractionation is much larger than 1.1 per mil. So it's actually okay for us. Okay, so the real way to do this kind of isotopic system, for example, for potassium isotope, you had to use a high precision multi-collector ICP-MS because potassium has the mass of 41, right? For those of you who knows a little bit about ICP-MS, how do we get the plasma sustained? Yeah, we use a thing called argon, right? It's argon sourced. So argon hydride, right? Argon 40 plus H is 41. So this is hard to do it on a multi-collector since we are measuring potassium 41, right? So we need a much higher mass resolution. It's actually 41.02 something, right, versus 41.12 something, right? So then you can actually distinguish those two. As you can see, those potassium isotope method, high precision, was only developed a couple of years ago. So this is a more newer isotopic system we are still exploring. So keep tuned. We may have more result later. Okay, so hopefully now you know a little bit about the techniques, and then it's actually taking a long time to get samples purified, dissolved, purified, and work, and then doing those fancy ICP-MS analysis. We want to understand what kind of questions we can actually use those tracers for, right, to study Earth's processes. To be honest, we spend, as an isotope geochemist, we spend probably a majority of our time trying to understand what is causing the isotopic fractionation, right, the mechanism, right? But I don't want to bore you too much to the details since you can read the papers. I want to show you some exciting applications about tracing weathering change through Earth's history. So that's one of the good things, right, coming up. So weathering. I talk about too much about weathering. What is weathering? You have anything on the surface of the Earth, they can react with precipitation, right? Plus CO2 is carbonic acid. The acid attack the rock. I don't know if you can see this well. When I was growing up in China, in elementary school, we know a thing called water can go through rock. But I didn't believe that. How can water go through rock, right? With time, right? So this is actually many years later when I visit a park in British Columbia. This is a natural erosion experiment, or a little bit weathering, because they put the same type of rock here, and then they put water, still same thing, for 50 years, 25 years, and 15 years, starting the water flow. So the only difference, starting same material, the only difference is the time, right? Hopefully, they control the water flow well enough within an arrow. You can clearly see water did go through rock. They leave a big mark for the 50 years, but even the resolution is not that great, right? So actually, weathering did occur in a lifetime of ourselves. We can actually see them, right? So and there's a lot of water holes. Of course, you can see them in rocks. But anyway, so the product of weathering, usually we have two important products. One, we call it the soil or regolith. So what's the solid thing left over, right? And the other is chemistry. A lot of the ions that actually dissolve in water that they can go with groundwater or real water, right? So those are in the water phases. So basically, chemical weathering is the breakdown of those primary minerals and rocks and forming secondary mineral, usually by clay, or the secondary minerals, and also some solids in water, right? So that's how we do this weathering study in the modern, that we focus on the regolith or the water study. Hopefully, we need to find an ideal laboratory to actually study what controls lithium and potassium isotope fractionation during weathering. So what's your ideal place? It's getting interesting. My ideal place is Hawaii. I want to do it in Hawaii when I was a graduate student, but then somebody published a paper on lithium isotope in Hawaii. So I said, okay, we went to the Pacific Northwest to study continental flat basalt. But anyway, long story short, my student was able to design a project that we work with soil scientist Oliver Chadwick from UCSB. He's the pioneer of the Hawaii soil study for the past 30 years, right? So, he studied the whole career there. So we can have a good suite of samples that we don't have to dig too much into the soil profile. And they already have some basic chemistry. And then we were actually able to do it in the summer of 2019, so it's before everything collapsed. So actually, the student Wen Shuai, actually, he can actually finish his PhD. That's good that we did it. Before. But actually, the reason why we choose Hawaii, I really need to justify this to NSF, right? Why we want to go to a place not for vacation, it's for work, right? Hawaii is a great place where it's made of basalt, pure basalt, right? It's ocean island. So there's not complication like the continents where you have a lot of source or rocks getting into your soil profile or the rivers. And also Hawaii has this well-studied stratigraphy. People have been doing this, the flows for years, and dating the flows are pretty clear, right? So it's a good place to design this kind of study. I call it ideal laboratory, right? The other important thing is it has a different climate in a very small time sort of geographic area. So if you look at this is one of the sampling spot we focusing on the Big Island, right? And then the trade wind is going the northeast direction, right? So this side of the island is pretty wet. The other side is the mountain shadow effect, so it's very dry, more like a desert. But if you just drive from here along the highways, like 40 minutes under, if you drive fast, but it's under one hour, right? And they produce soil profiles very differently, as you can see from the climate, right? We can assess the climate condition, how climate changed the flow, because both the lava were generated about the same time, 350,000 years ago. But the soil profile is really different, really thick, about 15 meters, and it's very wet side. You can see the vegetations are green, nice, right? Versus the wet, the dry side, we have barely some soil development, and the grass are not super happy, a little bit dryish, right? So we can look at the climate control on chemical weathering, right? So now good for data. Look at some data. So for example, what do we use to express lithium isotope fractionation? I forgot to show you the delta notation. Everyone heard of delta, right? A geochemist's way to be lazy. Instead of saying the fractionation is 0.001, we times 1,000, basically use the same standard and times 1,000, right? Now we have 1 per mole fractionation instead of saying a mouthful of 0.001. So this is what actually we found. This is not too much compared to the previous study. Kaolinite is a good indicator of how much secondary clay mineral form. So basically, in theory, we predict, right, more clay we form, there's more fractionation. So more clay actually prefers a lighter lithium compared to the starting material, right? So that's both profile. The yellow ones are the dry ones, the dark ones are the wet ones. So they both roughly falling on the same, but I'm not gonna say there's some complication. I gave you a very naive picture of weathering, right, in a closed system, right? In reality, it's not. Even in Hawaii, it's a dusty place. People have documented there's dust input from Asia, years ago. So it's not a complete closed system, but I'm just trying to tell you a little simple story. On the first principle, the climate did control by, depending on the clay mineral formation, right? How much clay formed. And then the faster the clay, and then you get more fractionation. So basically that confirms previous understanding of secondary mineral formation prefer the light lithium. So we're getting a little bit to the fractionation mechanism, right? But I wouldn't say some bond coordination number. How about potassium? Potassium is a new one that we haven't really discussed a lot previously. But we noticed, actually my student actually noticed that the behavior between the wet and the dry profile is very different. So the parent basalt is more like in the middle, something about negative 0.4. And then the wet one, wet profile, you call it, or humid profile, they all seem to have lighter fractionation, right, in the soil. This goes similar to lithium, right? We think clay prefers the light ones. And then, but then in the arid area, it's actually the opposite. So what happens there, right? It's a kind of mystery. We guessed because in the drier area, we have higher pH. That means more surface absorption going on, right? So we guess maybe heavy isotope actually prefers during the surface absorption processes. So we can have higher potassium isotopic composition versus the light is actually the clay formation and the incorporation processes. So how do we test this, right? We don't want to do clay formation experiment in the lab because it's taking a long time. Because as maybe many of you know, right, low temperature clay formation in the lab takes a couple months for one set at least to do. So we thought out, okay, we can do absorption experiment, right? Absorption experiment turned to be really fast. You can get a steady state within two days. So I'll show you this minutes, just keep you awake. If you count how many minutes in this talk, and I'll treat you something next time I see you in a conference. 1, right? I'm not going to remind you later. Anyway, so my student actually was smart enough to design a very simple tube experiments. Basically, he washed the clay really, really well to get all the surface clay out and put some potassium-rich solution and then let them react under different pH, different mineral condition, under different ionic strengths, right? To see if the absorption is actually prefer the heavy isotope, right? So that's his result. I'm just showing you a simple one. You can read the paper for a complicated story. But in general, so this is a type of minerals versus the potassium isotopic fractionation. So as you go by the higher degrees of weathering, right, you have more kaolinite as smectite. The absorption ratio is actually increased, right? 100% is the maximum you can do. Usually it's not real, right? You can't have 100% absorbed on the surface mostly. As the absorption going on, right, the solution is, we have to measure the solution, right? The solution is getting lighter, right? That means the more absorption, the lighter the solution. So that means the clay should be heavy or light? Heavy, right, right, good, right? So the solution is lighter, right? So mass balance, right? The whatever the solid phase they interact should go up, right? So okay, that's cool. So that at least one of the first experiment that explained why we see those two kind of contrasting behavior in this arid area where there's a lot of higher pH, where we favor absorption going on, right? The lower pH one is just the normal clay formation, which this is more typical weathering profile. I wouldn't say this is very typical, right? The pH is really high, and we even have like a carbonate nodules in those soil. So it's pretty dry, evaporative, and high pH environment for the dry profile. Anyway, so that's some fun in Hawaii. The other perspective, okay, just emphasizing heavy potassium maybe associated with absorption. We're not saying it's a 100%, right? It's a laboratory experiment. It's a very kind of natural, sort of simple explanation, but at least it's probably more absorption dominant, I would say. And this one is incorporation dominated mechanism. So after we know that, maybe we can use the potassium isotope to specific settings to study weathering in Earth's history. He's super interested in plants. I wasn't too much, but anyway, he sampled some plants from Hawaii and trying to understand the fractionation. Because I was told lithium is not a nutrient, therefore no isotope fractionation in plants uptake. Oh, we are really wrong. So actually there was fractionation, at least in those Hawaii plants that he studied, as actually the plants, as everybody else, is lazy. So usually they prefer the lighter one. So preferentially taking the lighter one compared to the heavy one. But I'm not going to bore you with the detailed, and you can read the paper once it's already published. For potassium, this is not a surprise, right? Because potassium is an important nutrient, so we were expecting some fractionation. Although the fractionation is actually more complex than we thought. I'm not a organic geochemist, so I don't know too much inside of the plants, but at least the bottom line is, seems like the roots are still lazy. They prefer the light potassium. But then within the plants, they have like a kind of distribution with leaves, prefer the heavy one, but then they die, they go back, and they becoming the light one coming back. So it's like a whole circle. So I just want to emphasize that vegetation is important for both lithium and potassium isotope. So when we study rivers, for example, we can't ignore their effect, right? Because for soil, it's probably okay, or it's eventually even out. But for rivers, that actually fast residence time, so it may, especially seasonal variation, right? It may matter. Good. Not sleeping yet, right? Just do a little bit summary. Both lithium and potassium isotopes seem to be definitely weathered, sort of so fractionated during chemical weathering. There is a source control that I didn't say too much because we're focusing on the basalt, so it didn't have too much source variation, although there is Asian dust from other radiogenic isotope and mineralogy evidence from previous studies, so I didn't emphasize. But we do emphasize the climate control, right? Climate ultimately controls what type of clay mineral and the pH of the soil profile, and therefore controls the isotopic fractionation. And then vegetation is actually important, right? So we can't ignore the biological cycle, although my limited knowledge of biology, but we had to go on. So looking forward to learn more from more bio perspective. So lithium isotopes seem to be could be a good tracer for chemical weathering. It's mostly chemical driven. Potassium isotope may need a little bit complication since the direction of fractionation kind of goes a little bit opposite during the extreme pH condition and also the bio effect. And also because it's a new tracer, so we haven't used it for big Earth history study yet. So I think this is probably a lot of the people are very interested. Can we use those isotope tracer to study weathering change in Earth history, right? So I'll show you one example. Maybe this one will ruin you because the title of this paper, you can see, is not what we thought. We were actually trying to develop this project to study chemical weathering change during the one of the big five, right? The late Permian to earlier Triassic transition. Actually, the bottom line is we actually found maybe enhanced reverse weathering. Let me explain to you later what they mean. So this was pioneered by my very first PhD student, Chen, and very first postdoc, Xiao-Ming. So they did the hard work for those. I'll tell you some story. So that's another meaning. Surprise, right? So about co-evolution of Earth's surface, right? The life and Earth, we have intertwined relationship between life, modify the surface, and the surficial environment actually sustain life. So a lot of the things goes back to especially the big five, right? Big five mass extinctions, except for the ones that kills the non-avian dinosaurs as a KPG. Most of the storylines go this. Sorry for the specialists, I'm generalizing this scenario. So massive volcanism causing a lot of CO2 release, right? A lot of CO2 release causing increasing chemical weathering of those silicates, too much nutrient delivery, getting hot and getting acidic, a lot of acidity in the water, and kind of deoxygenation a little bit in the ocean, right? Too much nutrient, and then kill, right? So something like that. So it's kind of overall scenario. So we decided to focus on one of the big one that kills about 90% of marine life at least. Throughout the Permian to Triassic boundary. So to study this, people have already used traditional tracers like strontium isotope. This is one of the good radiogenic isotope tracer. I think it's still pretty useful. Basically, this one can say if you have, simply explain this diagram is if you can have increasing in weathering, right? So you're supposed to drive this value slightly higher because the continental crust are usually more radiogenic, right? So you can have more radiogenic value. And then if you have a lot of hydrothermal input from the marine, then your value goes lower. And so the fluctuation of strontium isotope curve in the ocean can indicate what continental weathering flux change, right? At least that was the thing, right? So you can either study those fossils, like carbonate fossils, like brachiopods, or carbonate rocks, or those conodon kind of samples, phosphate samples as well. This was actually a well-studied field, as you can see from the resolution of the curve, right? There is more study in this strontium isotope. So the lithium isotope actually only start about 10 years ago with high resolution. So this science paper is actually very one of the most famous lithium isotope paper, right? So they try to use lithium in foraminifera, a fossil, to represent seawater over time, at least through the Cenozoic, right? So this is actually the ones they produced now 10 years ago, right? They have seen a dramatic increase since about 50, 60 million years to the current, right? There is about 7 to 9 per mil, actually, increase, right? That kind of goes well with strontium curve, right? So that goes back to the argument that maybe that's increasing, tectonic uplift of the Himalayas, increasing the weathering, and then therefore you have those increasing isotopic signatures in the ocean, right? That's one mechanism. So I use this, our kind of thing for lithium isotope is enriched in silicates, so it's good for silicate weathering compared to strontium isotope, where people argue about that increase could be due to increasing weathering of metamorphic rocks, right, in the Himalayas. That could also kind of increase strontium isotope, not necessarily continental weathering flux increase. But is this true? I don't know. So there's some debates about that. I'm not going to bore you with the detail, but our recent result in my lab is we actually study a bunch of dolomite that you don't really assume they are primary, but they are fabric retentive dolomite. So we think they probably reflect close to seawater or the primary pore water, close to seawater composition. We were able to roughly reproduce what the 4M and brachypod record was, although there is some difference in this time window that I don't know the reason, maybe some diagenesis going on at that time for our record. But anyway, so it seems like this seawater curve has been reproduced at least since the Neogene, right? So there is an increase, right? So it seems like lithium isotope could be a good tracer for weathering. Although the story is not that simple, right? If you look at the modern marine, right, pool, that seawater isotopic composition is about 31, pretty homogeneous. If you analyze the seawater from Hawaii, or you analyze the seawater from Indian Ocean, same, 31. So it's really the same conservative element, right? But then you actually have two important components. One is so-called the weathering, right, the riverine input. The other is hydrothermal input from the bottom of the ocean, which is, I call it the missing pool, right? Every time you don't know something, you say the hydrothermal, right? So because this part is really hard to quantify, so we had to, but we still need to understand a little bit better. The other output for lithium is so-called the reverse weathering. So reverse weathering is basically the formation of orthogenic clay in the ocean, right? That actually takes lithium and potassium out of the ocean and sequester them into the sediments. So the assumption with that curve I showed you, right, is both the hydrothermal and reverse weathering doesn't change, right? Only seawater change is due to chemical weathering. Then you can make it work, right? So it's almost like a circular logic, right? We see this increase in seawater. We assume the other two doesn't change. And then, of course, it's chemical weathering increase, right? So that's a little bit that. But they do have good evidence, maybe through the Cenozoic. There wasn't a strong evidence of hydrothermal or reverse weathering change significantly, so that we think most of the change was from chemical weathering, right? So that's one argument there. But before we actually use our sample, because we are kind of maybe ambitious, we try to use this to even earlier Earth, right? A little bit earlier in Earth's history, like we talk about the Permian Triassic, right? First, we had to address this elephant in the room, right? Do we actually get in seawater composition, right? We can't fly back in time travel, right, to sample the Archean or Phanerozoic seawater, right? So we had to use some proxies. So all the proxies had their own problem, right? Marine carbonate is one of the field, maybe many of you knows, has strongly debated. One of the anonymous reviewer can always say, how about diagenesis? And then you're kind of hard to do. So diagenesis is later, formation of the rock reactions that actually can modify the original signature from the seawater, right? So it may not represent the seawater signature. So that's always an enemy. Actually, the other one another elephant that I want to address is the chemistry process is actually not that simple as you thought, right? Our friend is our enemy now, because our friend was the lithium is enriched in silicas and low in carbonate. But then we're now trying to analyze marine carbonate to reflect seawater. So we had to actually find some lithium in those carbonate. Hopefully those lithium are not from silicas. So this is a little tricky job. So this was what I put my first student Chang into this. I said, go do this project. It's going to be easy, right? But then she developed this very kind of complicated leaching protocol so that she can actually a little bit more confidently getting maybe the signal I was analyzing is from orthogenic carbonate, so not from the dirt, that we talk about. So that took a couple years to get it. Actually, one of the secret is not only you had to use vinegar, very pure vinegar though, right? Acetic acid. You had to use very pure acetic acid to attack the rocks to make sure you get a carbonate component. Also, we had to use filters, because the traditional people only say, we filter them and then centrifuge them very well, right? We take the clear solution, clear from the top. It turned out the clear solution was not clear at all. So they have like small particles of silicates. So that's why she came back every week with different rare earth element pattern in her result, and we can tell there's a different mixing of clay minerals in her solution. So after she used the filter, then we were able to get a consistent result. So that's one big take-home message, because in our field, especially in those trace metal geochemistry, people not talking too much about that. So most people just get a clear solution. Okay, so go back to the science question, right? What kind of samples we can take to solve our, the whole Permian to Triassic question? We want a global distribution, a little bit of the marine carbonate that represent the global ocean, hopefully. And also we want to, to be careful with our bulk carbonate, because the bulk carbonate has a little bit issues, right? As we say. We had to screen them very well. First, we need a pure carbonate unit, right? We roughly, ideally, I would say 90% of pure calcite carbonate, but sometimes it's hard to get that pure. We also had to micro drill, and then we actually had to do very vigorous diagenesis test, especially late diagenesis. As you can see, barely half of them passed our geochemistry, petrology, and stratigraphy diagenesis test. The other thing is we use those little guys, brachiopods, the fossils, to cross-check with our bulk carbonate, right? Because many of you know that they are a little bit cleaner in a way to reflect seawater, because they have been documented in the modern seawater that they have similar fractionation, or at least the same offset from the seawater. So that's what we need. Oh, ready for the result? Surprise, right? So if we look at the strontium isotope, we want to do the strontium isotope to actually tease out diagenesis, right? One of the fewer ones may have, supposedly diagenesis, because our samples are in squares and the previous published result are all the circles. So actually we grade mostly well, but then there's a few diagenesis samples, right? But then at least we have consistent record to the bottom line. We use the same leaching method and do the lithium isotope. Ready for the surprise. This is not exactly the curve I was envisioning when we designed the project, right? There was two, I would say there's a dip that's probably reflecting the hydrothermal. I'm not gonna talk too much, but I think the most distinguished one that everybody probably can see is this one, right? There is a 12 per mole decrease in terms of lithium isotope. And that's actually happened before the PT mass extinction. It wasn't at the mass extinction. So this is between 256, 255. Anyone knows the time for the PT boundary? It's about 252 something, right? So it's actually at least close to 1 million years before the mass extinction, at least the major mass extinction event, if you believe there's multiple pulses. But anyway, so this is the thing we want to focus on. Why we see this drop? We didn't expect that drop during that time. In addition, if we compare them directly with our strontium record, during the time of this drop, there's not much strontium isotope change, right? So the weathering hypothesis doesn't make sense, because there wasn't, first, that we wasn't expecting there's a weathering change at that time. And also strontium isotope doesn't show any changes. So why do we see the lithium isotope change? So we kind of hypothesize, maybe it's reverse weathering. This concept could explain it, because if we use reverse weathering, the marine orthogenic clay formation, if they can take a lot of lithium out of the ocean without causing too much fractionation, we can actually decrease the seawater delta lithium value, right? Is that good? It's a hypothesis, right? So what's the evidence? Not too much, but I'll explain a little bit what's exactly reverse weathering. So this concept was actually originally proposed in the 1960s. Why it's called a weird name, reverse weathering, right? It's from this reaction you can tell. Basically, the effect of the silicates plus aluminum hydroxide and plus some alkaline element, they form clay mineral and producing CO2. So this is the reverse of the chemical reaction of silicate weathering, right? They're producing CO2 instead of take CO2, right? Chemical weathering of silicate rocks actually take CO2. So this one release CO2. So that's why it's reverse weathering. I think, because the name is weird, reverse effect. So the net effect, as you can see from this simple chemical reaction, is one, you have a lot of clay formation, and also you reduce a lot of the alkaline earth element and silicon in the ocean. Also, you produce CO2, that means decreasing pH, right? So that's the consequences of that. So do we see that? It's really hard to see evidence, but we did find a chert gap about the same time. I don't want to say the chert gap is the gap globally, because we found there was the time period where before the mass extinction or a little bit around the mass extinction, we do see there's little deposition of chert. So those creatures like radiolarians, they use the silicon in the ocean and then they make chert, right, deposit. And also this actually coincided with some extinctions of radiolarians in the late Permian. So this is upper Permian picture, right? The late Permian wasn't having much. So the theory is maybe we have a lot of clay formation. We use a lot of the silicon in the ocean. So we're taking those silicon out of the ocean. Therefore, those creatures doesn't have enough silicon to work with. Not like the modern ocean, we have diatom, right, to maintain the silicon cycle, that we have a lot of silicon in the ocean, right? So that's just one potential evidence. Although I had to admit the time is not super well constrained because it's based on stratigraphy, so it's not very accurate age dating. The other evidence I think is we found a lot of clay in the same time period. These clays are indicated by the gray bars. There's a lot of clay formation, although you can argue, well, those clay may coming from the continents, so not necessarily orthogenic clay formation. So therefore, maybe not evidence of increasing marine clay formation at that time. It could be coming from continental clay. But at least there's a lot more clay at that entire period compared to the later, after the extinction. So that's our running hypothesis. So hopefully, to confuse you, I told you lithium isotope could be a good tracer for chemical weathering. And then I showed you one example. It's probably not, right? But I want to emphasize this part is not, right? This part we think is due to reverse weathering reaction in the ocean. But then there are other two parts that maybe one is associated with Tethys ocean opening, so that come with increasing hydrothermal activity, so they could bring down the lithium isotope. And the other part is the increasing chemical weathering in the earlier Triassic. That's after mass extinction. So this one actually goes well with a strontium isotope record. So I don't want to say it's not that, but it's overall. Anyway, okay, so summarize what we learned about lithium isotope fractionation. Anyone remember anything? At least you probably remember the clay prefer the light lithium, and then water phases prefer the heavy one, right? So that's in general the case. And then the vegetation actually prefer light lithium. Okay, you can remember it, everyone is lazy. So for potassium isotope, I didn't talk too much, but we did some synchrotron work that actually looking at the chemical structure of how potassium is actually coordinated with oxygen in their clay structure. So we were able to demonstrate that actually those secondary clay minerals did have high coordination number, right? So compared to liquid phases. So the lower coordination number usually corresponds to high bonding energy, right? So that prefers the heavy isotope. So that cause of explaining why clay is actually having lower value compared to aqueous phases. Although we can't do the absorption part, but we did a laboratory experiment for the absorption that demonstrated absorption can cause heavy ones compared to the liquid phases, right? Good. And then the vegetation prefer light potassium. So if we look at the global potassium cycle, I think there's a lot to be done, right? We try to explain why real water have heavy isotope compared to rocks due to weathering, and then the soil actually forming usually prefer the light isotope. I think we got this. And then we actually do need to worry about biological processes in the rivers. The other important thing, both for lithium and potassium isotope, is also my research direction, is we want to look at the reverse weathering in a more detailed scale, so we can study that. Okay, for future, hopefully, I'm still looking forward to sharpen our tools, right, to understand the fundamental fractionation mechanism in those isotope systems and their global cycles. I'm also excited of the new like ChatGPT can write your paper now, right? So, but then we should embrace this kind of age that we can use the existing data, and if we have good ideas, we can actually take advantage of not only doing laboratory work, we can also use big data approach to study the processes that we normally do before, right? With enormous amount of data available. And then I'm very interested in other planets as well, including maybe potentially Mars sample return many years later. For those of you who are your students, you are at the right age for that, for a couple years later. Right, so I want to acknowledge my current lab, and then I focus on the 2 students and 1 postdoc work for this talk. But I do want to say we already have current students, they are working on very diverse kind of topics, from tracing continental weathering through Earth's history, to marine orthogenic clay formation, to weathering on Venus. So stay tuned. Even I don't know too much about weathering on Venus, but Alex seemed to convince me that that's an interesting reaction. It's still weathering, although it's super hot and not very, no liquid, very dry. So we'll see what's going on with that. So with that, I'll thank my collaborators. I see, thank you, haven't fall asleep. So thank you for being here, and Zoom people haven't fall asleep yet. And that, I'll say, yeah, thank you.
Any students, excuse me, any students have questions?
Yep, that's good. Clear as mud.
Any other question or anything online, Matt?
Nothing online yet.
Okay.
Oh wait, there's an applause, not a hand raise.
Yeah.
So I've also heard about lithium. So I've heard about lithium to calcium, I think, as a temperature proxy. I wonder if if you know anything about how those two interact. Are people using them together at all, or does the removal of lithium affect your proxy at all?
That's, yeah.
Repeat the question.
Oh, I had to repeat the question. So how about the lithium and calcium? Usually they use a ratio, right? Lithium-calcium ratio in a lot of the biogenic carbonate for paleoceanography, or, yeah, I'm not sure. I think people use them empirically, because I asked the same question to those people who presented those proxies. I don't think they have a fundamental understanding of what exactly incorporated. So it may depend on temperature, and also depending on, of course, mineralogy, right? If you have aragonite versus calcite, so definitely it's going to change. So it's a little bit complicated, but it works empirically in a smaller time period, and also usually those people usually study the same species, right? So it's actually good. And then the thing called vital effect, I'm not sure you're familiar with, right? Because a lot of species you had to do this sort of calibration. Otherwise, you just roughly go in there, and then it varies from species to species, because different animals or microbes, they build their shells differently. So I wouldn't say a straightforward record. Yeah, so we need to do a lot more work on experimental. Maybe you grow some microbes, forams or whatever the proxy you're using, and then see how they react. So for lithium isotope, actually, we have people trying to do laboratory experiments, but also the kinetics is always a problem, right? Because in the laboratory you can do things really fast, but then it's not a reality. But then you need to graduate, so you need to accelerate a little bit. So we need to find this good zone that we can actually characterize or calibrate them, maybe in the modern ocean or in the cultured environment that you can see it. So we actually did some potassium isotope work also in cultured environment to see how they change in corals. So we do see a temperature dependence as well. Although this temperature what it means is a little bit hard to do, right? Because we do notice there is a lot of organics in those biogenic carbonate. Unfortunately, a lot of potassium actually enriched in those organics. So, I mean, that's depending on how much organics you have. Then that's an issue for potassium isotope, maybe in the past. But if you have older rocks, maybe you don't have that problem. But then the modern ocean, biogenic carbonate, you always have a lot of organics. So depending on how you use it. So you need to be extremely careful. I like the question you asked because you're focusing on the, why this tracer works, right? So it's not very well demonstrated, I think. A lot of them are empirical. So, yeah, thank you for the question. Great.
Mark, and then Rick, and then Ben.
Hi, great talk. So I think a great location to study reverse weathering and lithium isotopes would be at the bottom of the seafloor, with maybe close to hydrothermal sites. Do you know the latest findings to the results of people who collected at the bottom of the seafloor?
Yeah, that's a very good question. We actually want to find a suite of samples that actually exactly like your description, right? We want to be far away from the continents. We don't want all those continental detrital clay and only clay that form under the ocean. Yeah, I think somebody did a study of smectite years ago, focusing on lithium isotope. Somehow she published the abstract, but then there's no paper coming because I think one of the reasons is she studied like smectite through Earth, not Earth history, but at least a Cenozoic timescale. So she couldn't reproduce the same Mizra curve, so the same increasing curve. I think my impression of her clay was flat. So I mean that has some implications. Maybe the clays wasn't exactly reflecting the seawater. Maybe depending on during the clay formation with the seawater, maybe there is some fractionation mechanism that we don't really know, right? Because it depending on what type of clay you form. So maybe that's one. And then it's possible that the seawater curve was wrong. Although I don't know. Like before, I was very curious about that as well because considering how little sample they had to do. Right, the forum sample. Right, the guy I met, he said he spent like 5 crying years in the lab picking the foreign vessel. For some of you already nodding. Right, you had to collect a lot. There's some possibility of they are wrong, but it seems our dolomite was able to. It's independent record from totally different settings and totally different mineralogy. They seem to kind of line up a little bit. So I do see there is an increase, or at least neogen. So maybe that's the smectite clay has some potential issue as well. So it's not very well designed. So I would love to know whoever can come up with a suite of clay mineral that's you already know what's the clay. Maybe it's good to do the mineralogy. It's really hard to find like pure orthogenic clay, right? Because all the clays are reworking from the previous. So it's a hard question, but I think we need to go there. Well, the other one we are trying to do is other lab is we try to synthesize some clay. But then maybe synthesis is too ambitious. Maybe we'll try to do some transition because it's hard to get crystallized clay. So we may have to do some synthesis experiments. So we are actually in the planning of doing that. So stay tuned. Maybe I can answer more. We are hopefully on the frontier of that. So we'll see.
Rick. Yes, thank you. Great talk. Have you done the mass balance calculation to determine how much silica you have to remove from the ocean to give you your lithium signal?
Yes.
5 million years ago?
Yeah, that's a good question. How much, right? And how much CO2 we can produce? We actually is actually currently working. Our previous model didn't do that, so a lot of reviewers actually, when we published this paper, also asked the same question. So we are working on the second paper that we're trying to do a reduced version of the CGNE model that couples carbon, silicon, lithium model. So we'll do that, but I haven't really heard back yet from our modeler. So we'll try to see, kind of having some quantitative estimate. Yeah, that's the next step to prove, or at least to see if it's reasonable. And also we are excited to see how much CO2 that can produce, right? If that's one of the mechanisms that we can cause a little bit of acidification and even increasing CO2. Doesn't need too much of how that compare to like the Siberia traps, right? So we'll see. So good question. Yeah.
And then, well, James or Ben?
Oh.
Yeah. I think you're first, but don't check.
Oh, okay.
Thanks. So I was just wondering what actually drives reverse weathering, and why is there a reason why you think it might have increased at that around the Permian Triassic?
Yeah, that's a very good question. Even reverse weathering in the modern ocean, it was popular not popular, it was proposed in the mid 60s. And then there's like people almost forgot about it for like 4 decades. And then now we're starting to really want to see, as Mark also said the same question is, where do you go to find this good samples, right? Natural laboratories, like a weathering equivalent in Hawaii, right? So how do you find out, an ideal location that you can actually do it, and you can find the same mineral formation, hopefully, or similar dominant mineral at least, right? And then they can through time. That's one, and how they form is actually very complex, even in the modern ocean. So recently we had a potassium isotope study on glauconite. So a lot of glauconite formation on the continental margins is actually believed to be associated with reverse weathering. So we're actually trying to quantify how much potassium can be sequestered in those glauconite, and maybe use, on the contrary, in the later, then we can use the potassium isotope to trace the reverse weathering, how much clay, how much glauconite formation it was in the Earth's history. But yeah, the mechanism, it was only a chemical reaction proposed there, and then there wasn't a lot of study. There was a study in the mid 95 on the Amazons. They studied the continental margin sediments into the ocean and studied also sort of the reverse weathering. And then there wasn't much until very recently, so more people are starting getting interested. So yeah, I think there's more chances we can do more study on the reverse weathering. So if you're interested, we can keep talking more about the details. Yeah, I don't know too much about the details other than, this is a potential mechanism, right? Oh, Ben.
I think my question is similar to James's. I was wondering, that was a great talk, by the way.
Oh, thank you.
Thanks. So I was wondering about reverse weathering through Earth's history.
Mm-hmm.
So thinking about what James was asking, why at that moment was there an increase in reverse weathering?
Mm-hmm.
And are there other times in Earth's history when you would expect that to be the case? And could you go there and make those measurements? And Did you see that?
Yeah.
Summarize both questions for the online.
Oh, right. For the online, I forgot about that. For the online audience, so 2 people asking about, how the reverse weathering change in Earth's history. So what's the mechanism that causing potentially increasing reverse weathering in the ocean, right? So yeah, the mechanism part we haven't really nailed down, but I think one of the potential is temperature. So we were in a greenhouse period, but we were in the a later part of Permian. So the transition to ice house, it wasn't there. So it's still a little bit warmer. So that's one of the reasons the reaction is a little bit faster, and then the formation of clays are faster. The other possibility actually doesn't mean increasing. The other way to do it, probably not as dramatic, is actually we can change the type of clay formation, and then we can fractionate a little bit differently. For example, smectite fractionation turned to be smaller than kaolinite. So maybe the different type of clay we dominantly formed was eventually controlled by pH, temperature in the ocean. So that may be contributing as well. As for the record, it's really hard. I read one recent paper, they were trying to look at the glauconite distributions through the Cretaceous to now. Right, they found a time period where there's more glauconite formation, and then that goes to with maturity of more potassium in them. So I think we are starting to find more interesting samples that's probably more unique to orthogenic clay. Other than smectite is a little bit harder because it could be continental weathering and also the orthogenic clay. So we need to find the right suite of sample that probably more saying it's just orthogenic clay, which is hard, even in the modern ocean. So
I'm going to ask the final question since I'm the host.
Okay, you can.
So when you release the CO2 to the deep ocean, would it be a positive, negative, or benign feedback?
That's a good question, right? So you actually introduced acidity, right? So you first decrease the pH of the ocean. So that should be, sort of facilitate clay formation. I thought it's kind of more positive feedback in a way, if I had to choose. But then, but then you do release the CO2 to a saturation. You know, if it released to the atmosphere, then you could be also increasing continental weathering. And then you could deliver more continental clays into the ocean. Actually, having more starting material, maybe you could also increase the oceanic clay. So that's actually a very interesting point, that maybe we could have a sort of kind of one-way feedback that keep increasing the clay formation. But at some point we had to stop, similar as the atmospheric CO2 story, right? So positive feedback versus negative feedback. Yeah, it's hard to answer, but it's good. Good question
Well, let's
to think about.
Xiao-Ming,
Thank you.